Welcome to the third lecture video in our Class 3 time series of lecture videos. I hope you guys remember we talked about kinetic and thermodynamic control of reactions. We're going to talk about it again in the context of these conjugated dienes. You see, the points I bring up, they just keep coming back again and again and again. And yeah, through the practice that we get looking at these notes, listening to these videos, practicing the problems, doing the quizzes, eventually we'll be ready for the questions that we see on our exams for this class and our professional exams too, hopefully. So, reactions of conjugated dienes. Let's start out with A, reaction with some mineral acid like, say, HCl or HBr, right, HX. Here we go, right? HBr can add to alkenes. I think we saw this in the first semester of organic chemistry, Markovnikov addition, right? Generally, it is favored. Here we have a possible product, 1,2 addition. So we've added the proton of our HBr to carbon 1 and the bromine goes to carbon 2. We could also have 1,4 addition where somehow the proton got added to carbon 1. But then we had some resonance form, right, of the resulting allylic carbocation system, which we'll see in the mechanism. And the bromide got added to carbon 4. Which is the more stable alkene? It's the one that has 2 alkyl substitutions versus the alkene that has 1 alkyl substitution. At low temperature, we prefer this 1,2 addition, 70%, right? We'd say this is under kinetic control because the secondary allylic carbocation is more stable than the primary allylic carbocation that this is produced from. This is 1,4 addition. We see 30% at low temperature. However, we know that this is the thermodynamically lower in energy alkene, and it is favored at high temperature, which makes sense because generally at higher temperatures, we tend to favor thermodynamic products. Here, 1,2 addition is 15%, and 1,4 addition is 85%. What do these squiggly lines mean? This means that the stereochemistry is ambiguous. This means that the geometry of the alkene is ambiguous. It's probably a mixture of cis trans favoring trans. Here we might expect racemic. Anyways, mechanism. Step 1, Markovnikov addition to give the most stable cation. So when we add HBr to one of these, either one of those pi bonds, we're going to prefer to form a secondary allylic carbocation first, right? Versus what? A primary non-allylic carbocation. These just simply are not allowed, right? That's why we have a circle with a line drawn through it saying, no, we don't generate these. We can generate primary allylic carbocations. Those are stable enough to exist in solution, but these are not. What next? Well, of course, we know that for our secondary allylic carbocation, we can have resonance forms associated with it. So our bromide anion can attack either that secondary allylic carbocation or the resonance form is, lo and behold, a primary allylic carbocation. That's legal. So which of these intermediate cations is more stable? Well, now it's not the degree of alkyl substitution that controls that. It's the electronics, right? The fact that our secondary allylic carbocation has more hyperconjugation stabilization. So this is more stable in terms of an intermediate, which means there's a lower activation energy pathway for our bromide anion hitting this when the reaction is under kinetic control. That's why we get 70% of this product, right, racemic, under kinetic control. But at higher temperatures, we prefer forming the thermodynamically more stable, mixture of cis and trans dialkyl substituted alkenes. And that happens when our bromide anion hits or substitutes on that primary allylic carbocation. So beautiful Markovnikov addition. Here's a picture of the energy versus reaction coordinate diagram. We have the reaction coordinate on our baseline. Let me move this camera up just a little bit. There we go. Now we can see it all right in its beautiful glory. Here's our secondary allylic carbocation. The activation energy for substitution there is lower than the activation energy for substitution of our bromide at the primary allylic carbocation resonance form. Even though, right, our dialkyl substituted hydrocarbon is lower in energy than our monoalkyl substituted hydrocarbon, we form this faster under kinetic conditions, right? And yes, these resonance forms really aren't real, so to speak. It's just that in the molecular orbital diagram, the p orbital on that secondary carbocation position, it's just, it has a larger coefficient is what we would say. It extends out into space a little further, so it's easier for our nucleophile to hit it and interact with it versus the p orbital on the non-bonding, molecular orbital for that allylic system on that primary carbon. So hopefully this energy versus reaction coordinate diagram makes this more intelligible. Just a few more minutes of me talking, and then we'll cut this video, truncate this video short, and just leave the rest for the next video. In summary, at low temperature, 0 degrees C, the product ratio is determined by the difference in activation energies. We prefer the lower activation energy pathway, which is the secondary allylic carbocation. The reaction is said to be under kinetic control under those conditions. At higher temperatures, like 40 degrees C, the product ratio is determined by delta G. That's the difference in, product energies. And the reaction is said to be under thermodynamic control. And I think we'll quit there. In the next lecture video, we'll talk about the reaction of conjugate diene with a diatomic halide of some sort.